This is Group 4. The reporters, Indis, Galang, Lumayag, Guiñares, Momongan, Gumera.
Good day everyone, I'm Cadet Lee Aurel Guiñares and I'm here to discuss the law of flotation, effects flooding, and survival requirement IBC and SOLAS. So, law of flotation, the weight of the floating body is equal to the weight of the fluid displaced by the immersed part of the body. Let me give you a simple example. A floating drum and the water. This drum is floating because the weight of the drum is equal to the liquid that is being displaced by the immersed part of the drum. So if I want to sink this drum, I'll have to increase the weight of this drum. But I did some fixing to it, and if I keep on adding some weight, there will come a point when the weight of the drum would be more than the weight of the liquid that is displaced by the culprit drum, and that is the point the drum will sink. And similarly, when the ship gets damaged, the theoretical displacement of the ship is still the same. That means the weight of the ship is still same, but the buoyancy changes because the compartment which is breached, that is no more a part of the ship. As you can see the diagram, the area of just flooded does not really help in providing the buoyancy which will keep it afloat to really fill the suffix. Imagine being the swimming pool floating using this particular drum. Everything feels fine as long as there is air in the drum, but soon the water starts to flood in because the cap goes off. And this is what a flooded ship feels like. Water starts to come in, and as the water is going inside, the buoyancy of this particular drum is going away, but the weight is still the same. And soon what will happen is, if you are holding into this drum, you will go down with this in the swimming pool, because then there'll be only weight without any buoyancy. Let me come to the point what you're looking for, and I'll come back to the story later. Now there is a survival requirement which has been said as per SOLAS, and this one has the IBC code SOLAS. And IBC code said, okay, if the ship gets damaged, this is the minimum survival requirements. That means if the ship is capable in maintaining these conditions of 8 is damaged, then I can say that the ship is safe and it will be approved. And these are the survival requirements for all tankers as per SOLAS. And if you read carefully, the IBC code and SOLAS say almost the same thing for the survival criteria of the ship. The part number 1 says the final waterline taking into the account sinkage, heel and trim shall be below the lower edge of any opening through which progressive flooding may take place. Like air pipe protecting says the unsymmetrical flooding shall not exceed 25 degrees, which can be increased up to 30 degrees if no deck edge. Then it requires 20 degrees of positive stability beyond the position of the equilibrium, and the residual righting lever shall be at least 0.1 meter within the range of 20 degrees, and the area under the curve within this range will not be less than 0.0175 meter radian. So this is what the minimum survival requirement looks like.
Survival requirements booklet talks about. It talks about the distance from the waterline to the opening through which progressive flooding can take place. It talks about angle of heel. It talks about range of righting lever or GC curve. It talks about the residual righting lever, an area under the new GC curve. To select two specific points, is the hull of this drum, how far is it from the waterline? Because the closer it gets to the waterline, chances of progressive flooding increase, and thus the chances of sinking also increases. In any case, my range of righting lever curve, the length of residual righting lever, and the area under the GC curve would reduce. Finally, a condition in which I'm closest to the opening and the angle of heel is max, that is what I can easily select as the worst condition that I can have. So here's an example from the damage stability booklet from the particular ship. Condition 0301, the angle of heel, and this is 20 degrees, and the opening from the progressive flooding can take place is only 12 centimeters away. Is it important that you understand that sometimes in that damage stability case, the next opening from which the progressive flooding can take place is actually included in the calculation. So in that case, you would look for the next worst condition and check it out.
Good day everyone, my name is Charles Kent Galao and I am here today to discuss about the effects of bilging on the GM of the ship. To begin with, let us determine the definition of bilging. So what is bilging? This occurs when the ingress of water takes place into the vessel from a point below the waterline. Furthermore, what differentiates this bilging from flooding is that bilging allows the free flow of water in and out of the vessel, and while in the case of flooding, it is unable to flow out of the vessel. Here we have some basic terminologies that we will be using for the formula of Km. So Kg is your vertical height above the keel. GM is your metacentric height, the distance between the center of gravity and its metacenter. KB is the height of the center of buoyancy above the keel. BM is the distance of B to M, or the metacentric radius. Km is the distance of the metacenter above the keel, which we will be computing. So Km can be derived from two formulas. So Km is equals to Kg plus Gm, or Km is equals to Kb plus Bm. When a ship is bilged, we can say that the weight of the ship remains the same. It may have a hole in it from where the water can enter the ship, thus we are losing buoyancy. So as this occurs, the draft of the ship also increases, and every time the ship's draft changes, the water plane area also changes with it. Additionally, when the water plane area changes, the moment of water plane area around the center line also changes. So with this, we have a stability formula which can be derived as Bm is equals to I over V, where I is the moment of inertia around the center line and V is the volume of displaced water. So due to the effects of bilging, the Bm changes drastically while Kb only changes a little bit, thus affecting the value of Km. So we have the formula Gm is equals to Kb plus Bm minus Kg. As we can see from the formula, the Gm of the ship is directed affectedly. As Bm decreases, the Km also decreases, while the Kg of the ship remains the same. And the formula can further be simplified as Gm is equals to Km minus Kg. Since the Gm goes down with bilging, the righting lever Gz is also going down. So Gz is equals to Gm times sine theta. As the Gm reaches its lowest possible value, the chances of keeping the ship stable at any degree would be difficult, thus increasing the chances of capsizing the ship. So to summarize, the GM of a ship goes down after bilging of a ship due to the loss of water plane area.
Good day everyone, I'm the Cadet Angelo Lumayag and I'm here to discuss the subdivision and floodable length. So subdivision and floodable length follows along with what we are talking about with the flooding of a ship. Your ship has become damaged a bit and has flooded. What are we going to do? Obviously, we would like to try and restrict the flooding effects as much as possible. We can use watertight bulkheads to divide up the spaces in the ship and contain the flooding to the minimum possible number of spaces. One way to calculate how many watertight spaces you need to have is by calculating the floodable length of the ship. So first, in terminology, here's a little cross-section of a ship. You have a watertight bulkheads, which are just walls that are watertight. No water can get through this, lead up to a bulkhead deck, which is also watertight. You might recall that this was a Titanic's problem. It had a watertight bulkheads but not the bulkhead deck. So water was able to spill from one space to another. We no longer have that problem. If a ship is damaged, water will come in. It will flood, but flooding is restricted because of the watertight bulkheads and the bulkhead deck. But the question is, how many watertight bulkheads do you need? We can appreciate that probably more of them is good. but then it makes hard and expensive to make the ship. Sometimes you need to have a larger space because of cargo hold, so you need to figure out exactly how many you need to have. One way to do this is to use the floatable length. So floatable length is kind of weird concept. So got some pictures here, and it makes sense. In general, the floatable length is the length of the ship that when it's flooded, it will cause the ship to sink and trim, such that the margin line is immersed in the water. The margin line is an imaginary line. It is a minimum of 3 inches before the bulkhead deck, and what it means is it's a good bulkhead deck with the factor of safety put up on top. So if the margin line is submerged, it is the maximum amount of flooding that the ship can handle before it sinks. A couple of assumptions that the flooding is assumed to be beamed to me, that it goes from one side to the ship all the way to the other, and also the floatable length is centered at the middle part of the entire floatable length. Okay, you can do this analysis from one end of the ship all the way down to the other. So here I've got something started at the bow of the ship. This ship is flooded such that the margin line has been immersed, and big for this illustration, I'm not including the effects of trim, though when you're calculating it you will do. I just don't have it with these cartoons because it will look and it will get a lot of complicated. So what you do is you have the floatable length, and that will cause the margin line, like I said, to be immersed. You can take that floatable length and also plot it vertically. It's the same scale, and put that little dot there, right here. Okay, you can take this and then do the same things all the way down the entire length of the ship. You can see that it changes because the geometry of the ship changes as you apply it along all the way down here. If you connect the dots and you get the floatable length curve, and you can see that there are some regions of some shorter floatable lengths. This is because the ship trims. So if there's bunch of flooding up in the bow of the ship will trim bow down, and that will immerse the margin line faster. Similar with the stern. If the stern starts to dip down, that the margin line is going to get immersed much sooner in the middle, because the ship will sink in parallel. It will sink evenly. The full blanks are actually a bit higher. Relatively speaking, there's longer floatable lengths, and either this is because the bow and the stern of the ship are narrower than the middle part of the ship, the mid body. It really goes back to our calculation involving volume, right? So if you have length times width, well, if your width is much less, then you can get away with a longer length. Okay, don't decide a bow length curve. Remember that the floatable length centered around the midpoints of the flooding. Okay, you can draw these little triangles here. This will come into a little play, but generally speaking, you can draw floatable lengths, connect them with the triangles, and once you clean it, all of this is the floatable length for a given permeability, and this is a traditional way that you would see a floatable length curve with the diagonal lines. Then how it changes and going back down to the bow and the stern. There you can take that floatable length and you can do it for different permeabilities for those spaces, and you can either do it for I've shown here where it's one permeability for us going down the whole length of the ship. You can even do a piecemeal where, like you notice, different spaces of permeability of 0.9, 0.8, 0.7. You can do it in little bits and pieces. So what's the point of all that? You can use the floatable length to test your bulkhead locations. This is what you do to take a shape. You've chosen some bulkhead locations. You want to evaluate them to make sure that it's going to be sufficient to contain flooding for your ship. So you take the ship, overlay the floodable length curves. Remember, the floodable length curve is the allowable flooding that can happen for the ship before it sinks for a given permeability. You can take that, draw these little floatable length triangles for each one of these compartments, and this is kind of a confusing diagram at first. Look at it a few times, come back and watch the video again if you need to. It will start to make sense, but what it really is just a floatable length for each these compartments, and it's now it's not can continuously sort of like the original one, right? Because you restricted the flooding because of the bulkheads that you place in. There you draw the triangles for each compartment and each pair of compartments. Then you can trace over them. You can trace the actual floatable lengths for the one compartment flooding, that's the lower TL line, and then you can trace the actual double lengths for the two compartment flooding, that's the purple line, right? You can compare the actual and audible lengths for those highlighted lines to the allowable floodable lengths, which is the red line. Okay. For this case, because the purple line is completely underneath the red line, it means that this is two compartment ship. It means that any single bulkhead can be damaged to be taken out, and then the ship will sink. Not sink. Here's another example. Same ship, but now we have a fewer bulkheads, so we have larger compartments. We're overlaying it with its floodable length curve. Here on this different permeability, we take it again through the floodable length triangles for each compartment and pair of compartments, but now we have less bulkheads, we have larger spaces, and so the triangles are correspondingly larger. We do the same thing, highlight the lines for the actual floodable lengths for the one compartment flooding, and for the two compartment flooding, we see this part of the two compartments triangles is above the foot of a length curve. The one compartment triangle is all underneath, that's okay, but the little part is above all the allowable floodable length curve. So what it means is that this bulk is damaged, these two compartments are going to flood, and the ship is going to sink. So this is the only one compartment ship. So you can appreciate, right, that a two compartment ship is safer than one compartment of three compartment ship is probably safer than two compartment ship. But eventually you could put it in so many watertight bulkheads that you know any damage at all cause five of them to flood, and so it sort of defeats the purpose. So in evaluating damage stability, we can, in the old ways, it includes the floodable length, factor of subdivision, etc. So in new way is the safety of life at sea, or the SOLAS 2009, recommended probabilistic damage assessment. So that's all for my report, and once again, I'm Deck Cadet Lumayag, and thank you.
Good day everyone. Today we are going to talk about permeability of the bilge compartment, ship stability. So what is permeability? Permeability is the amount of water that can enter a compartment after it's been bilged. The whole of the buoyancy provided by that compartment is lost. As the water enters the hole in the compartment, it gives buoyancy to the vessel. Value of permeability is using the symbol of mu. As you can see, that is mu right there in the presentation. So let's continue. If the vessel compartment is empty, it gives 100% buoyancy. In an engine room, it gives 80 to 85 buoyancy. Grain-filled cargo hold gives a 60 to 65 buoyancy. Coal-filled compartment gives a 36 buoyancy. Lastly, filled water ballast tanks gives 0% buoyancy to the vessel. So take note that the higher the value of permeability, the greater the loss of buoyancy. Therefore, the value of permeability is directly proportional to the loss of buoyancy. Permeability can be solved by using the formula broken storage over the storage factor and then multiplied by 100. When it comes to permeability, the increase in draft when bilging uses the symbol X, and it can be solved using the formula V over A subtract a small letter a, where V is the volume of lost buoyancy over the area before bilging, which the capital A subtract to the area of bilge compartment, which the small letter a. When bilge compartment contains cargo, our increase in draft as X will use the formula permeability multiplied to volume over the area after the bilging subtract to the permeability multiplied to the area of the bilge compartment. So for example, a box-shaped vessel is 64 meters long and is floating on an even keel at 3 meters draft. A compartment amidship is 12 meters long and contains cargo having a permeability of 25%. Calculate the increase in draft in this compartment if this compartment is bilged. So the solution is, okay, let's answer it. So we know the length of the vessel is 64 meters and the length of the midship compartment is 12 meters. The initial draft is 3 meters. The permeability of the draft is at 25 Since the vessel contains cargo, we will use the formula for increase in draft with cargo is the increase in draft is equal to permeability multiplied to the volume of the buoyancy over the area after the bilging minus the permeability multiplied to area of the bilge. So permeability multiplied to 12 times 3 and times B, where B is the increase in draft, over 64 multiplied to B minus 3 multiplied by B, we can get 9B over 64B minus 3B. The increase in draft is equal to 0.15. That is the answer. So let's go to the next example. The next example is a ship is floating in salt water on an even keel at 6 meters draft. The TPC is 20 tons. A rectangular shaped compartment amidship is 20 meters long, 10 meters wide, and 4 meters deep. The compartment contains cargo with a permeability 25%. Find the new draft if this compartment is bilged. So here's the solution. This is another way of solving for the new draft if this compartment is bilged. In this example, the compartment contains cargo, thus we will be using the formula the same as the last example. We will get the buoyancy loss. We multiply permeability times the volume, and getting the volume, we multiply the dimension of the rectangular shaped compartment. 20 times 10 times 4, and then multiply by the density to get the buoyancy loss. So the answer is 205 tons is the weight of the water that has entered the compartment. We know how much weight has entered in the compartment using the TPC value. Using the TPC value, we can solve the immersing value. For every 20 tons, we have 1 centimeters immersion. We can know when the ship will immerse by dividing the buoyancy lost over the TPC. So the answer is 10.25 centimeters that the ship will immerse. So let's convert the 10.25 centimeters to meters. We will have 0.1025 meters, and then the 0.1025 meters to 6 meters. You have to add 0.1025 meters to 6 meters from the length of the old draft, and we will get 6.1025 meters as the new draft compartment is built. And that will be all. Thank you.
Good day everyone, this is Cadet Mundis, JL Rebecca E. I'm going to discuss the bale capacity and grain capacity. So let's start. Bale capacity and grain capacity. So this topic is divided into 4, and the first question is, what is bale capacity? The second is, what is the grain capacity? The third is the difference between the two capacity. And lastly, the grain in bale spaces or capacities. What is bale capacity? Bale capacity is the space available in the ship compartment where cargo is loaded in a package form. For example, bales, bundles, bags, drums, boxes, and many more. Here, this is the bale capacity. What is grain capacity? Grain capacity is the volume occupied by grain or any form of bulk cargo inside the cargo hold. So here, the grain capacity. The difference between the two capacity. The grain capacity is all the measurement are taking right to the plating, and all the allowance is made for volume occupied by frames and beams, while the bale capacity is a breadth taking from inside the cargo battens and the depth from the wooden sailing to the inside of the deck, while the length from the inside the bulkhead stiffeners is sparing if fitted. the easiest word, in most cases, bale capacity is less than the grain capacity. It may be equal, but not more than grain capacity. So you can compare the two picture here, the bale capacity and grain capacity. Lastly, the grain in bale spaces or capacities. So here, as you can see, this is the form of bale capacity and grain capacity. And the internal volume of a vessel is measured in two ways. So first, the total internal volume measured from shell plating to the shell plating and from the tank top to the underdeck of is considered as grain space. But this space is not only associated with the carriage of grain as such, but with any form of bulk cargo which could stow similarly, that is to say, completely filling the space. So, in Bisaya on tato, grain capacity is kanabitawang nasulod tanan, wala space na kulang, puro bitaw, puro ang pagsulod sa ship. And second, the internal volume of a compartment measured from the inner edge of the frames and from the tank top to the lower edge of the beams is considered as bale capacity or bale space. It is obvious that a solid cargo can be stowed only up to the limit of the frames and beams. Therefore, when measuring for general cargo, it is the bale capacity which taking into consideration. So, in Bisaya o nato, ang bale capacity is limitado lang siya. Depende kung makasya siya sa atong beams and frames kaysa sa grain capacity. We are the Group 4. That's all for today, and we're now signing off.